we're going to start with Dalton's law of partial pressure. So yesterday in lab, there were 3 series of calculations you had to perform. The very first in that series was Dalton's law of partial pressure. In lab, we took the barometric pressure, and the barometric pressure was equal to the vapor pressure plus the pressure of oxygen. You were able to determine the barometric pressure online. You were able to determine the vapor pressure based off of the temperature of the that you saw on the thermometer and the table that was in the laboratory. So when you took the barometric pressure and subtracted out the vapor pressure, you were left with the pressure of oxygen. The second thing that you were to use was the ideal gas law, PV equals nRT. And you use that to solve for the moles of oxygen. You then use stoichiometry to get to the moles of peroxide and then ultimately to the mass of peroxide. So multiple concepts were applied in yesterday's lab. Today, we're going to talk about 2 of those in greater extent. So Dalton's law of partial pressures is up first. When we say partial pressure, each gas applies its own pressure. If you think about the gases in this room, we have nitrogen gas. The nitrogen is zinging around the room, bouncing off the walls, bouncing off of you, bouncing off of other particles. Meaning that that nitrogen is applying its own pressure. We have oxygen. Oxygen is zinging around this room, bouncing off the walls, bouncing off of you, and bouncing off of each other. Meaning the oxygen is applying pressure. When we talk about partial pressure, we're talking about the amount of pressure a single gas applies compared to the whole. We can apply this concept. We can use the ideal gas law to figure out the partial pressure associated with any single gas, because it would be the pressure of that particular gas times the volume is equal to the number of moles of that particular gas times RT. You'll notice that the volume and the temperature here are constant. They are constant because the nitrogen and the oxygen are in this room at the same temperature, in the exact same dimensional space. So the volume and the temperature are constant. So the pressure of a specific gas is times its volume is equal to the moles of that specific gas times RT. Now we can take and rearrange the ideal gas law and solve for the partial pressure of each gas. We can say, okay, the pressure of gas A would therefore be equal to the moles of gas A times RT over the volume. The pressure of gas B would be equal to the moles of gas B RT over the volume, and so on and so forth. Now, Dalton's law of partial pressures basically says that the total pressure is the pressure of each of the gas components summed together. It's the sum of each of the pressure of the gas components. So the total pressure in this room is, it's going to be the pressure that the nitrogen's applying, the pressure that the oxygen's applying, the pressure that the carbon dioxide's applying, the pressure that the xenon's applying, and whatever else is in this room. You're going to add them all together, and that's going to be the total pressure, which just happens to be barometric pressure in this particular case. Questions about the concept of what Dalton's law of partial pressure states. Again, this is Dalton's law of partial pressure, but we can calculate the pressure of each component using the ideal gas law for that component. Now, substituting in to Dalton's law of partial pressure. Again, P total was equal to PA plus PB plus PC plus whatever ever continue. Where we were able to say PA was equal to the moles of A times RT over B. And the pressure of B was equal to the moles of B times RT over B. We can substitute in that portion of the ideal gas law for the pressure of each component. So remember that this is equal to the PA. This is equal to PB. This is equal to PC. When you do so, P total, therefore, is equal to the moles of A plus moles of B plus moles of C times the constant RT over B. In other words, we can take and get a pressure of the total room by knowing the moles of the gases in the room times RT over B. Questions? Now, what we have solved for, if you just look at the top of this, we have solved for the pressure of A is equal to NA RT over B. And P total is equal to N total RV over T. Meaning the pressure of A over pressure total is equal to NA over N total, because the RT over B, that should have been RT over B, cancels out. These cancel out. Now, NA over N total has a specific name, and it is something you're going to need to know for college chemistry too as well. And that is, it is the mole fraction. All mole fractions add up to the value of 1. What we have been doing, and I've highlighted key equations, is we have 4 key equations. Going back to slide number 1, P sub n is times V is equal to N sub n times RT. That would be the ideal gas law for a very specific component The second gas law, or the second arrangement, is Dalton's law of partial pressure, where the total pressure is equal to the pressure of component A plus the pressure of component B plus the plus however many components there are. The third is a variation on the ideal gas law, where we are allowed to calculate the total pressure if we know the total number of moles of gas using the ideal gas law. And then the fourth one is a mole fraction, where NA over N total is equal to the mole fraction A. So we can rewrite, if you go back to this equation at the top, PA over P total was equal to NA over N total. Well, if NA over N total is equal to the mole fraction, then PA over P total is equal to the mole fraction of A, or the mole fraction of B. Rearranging this equation, that means that the pressure for component A is equal to the mole fraction of A times the total pressure. You are going to see this equation again in college chemistry too. When you talk about the pressure of a solution, well, actually, when you talk about the pressure of a liquid that is that turns into gases, a liquid that readily turns into a gas, you'll use this equation. And you'll use a variation of this equation when you get into solutions. So let's look at examples. A 1 liter mixture of helium, neon, and argon has a total pressure of 662 millimeters of mercury at 298 Kelvin. If the partial pressure of helium is 341 millimeters of mercury and the partial pressure of neon is 112 millimeters of mercury, what mass of argon is present in the mixture? Okay, we're going to have to use a few pieces of information here. The first thing that we're going to have to use is we're going to have to use the fact that P total is equal to the pressure of helium plus the pressure of neon plus the pressure of argon. And we're going to be solving for the pressure of argon. So, P total was 662 millimeters of mercury. That's equal to 341 millimeters of mercury for helium plus 112 millimeters of mercury for neon plus the pressure of argon. Performing this calculation, you get a pressure of argon equal to 209 millimeters of mercury. But we need the mass of argon. So the next thing we're going to have to do is we're going to have to use the fact that the pressure of argon times the volume is equal to the moles of argon times R times T. Now we have to make everything match R. So I'm going to convert the pressure of argon into atmospheres by dividing by 760. And I get a value of 0.275 atmospheres. 0.275 atmospheres times the volume of 1 liter is equal to the moles of argon times 0.0821 atmosphere liters per mole Kelvin times 298 Kelvin. I then can solve for the moles of argon. And you get a value of 0.0112 moles of argon. But I wasn't asked for moles of argon. Now, why did I go to moles of argon? Why did I use the ideal gas law? Because I'm dealing with gases. And right now, my repertoire involves Dalton's law of partial pressure, mole fractions, and the ideal gas law. So I went to the ideal gas law and went to moles because that's what I knew at this point. There is going to be another option as we go, but now I'm going to take that 0.0112 moles of argon and I'm going to convert that into grams of argon using the molar mass of argon, which is 39.95 grams. Argon is equal to 1 mole. And you get a value of 0.449 grams of argon. Questions? Was there another way to solve this? Not really. Not at this time. Okay, let's look at another example. A sample of hydrogen gas is mixed with water vapor. The mixture has a total pressure of 755 torr, and the water vapor has a partial pressure of 24 torr. What amount of hydrogen is contained in 1.55 liters of this mixture at 298 Kelvin? Okay, I have two gases. I have water vapor and I have hydrogen gas. So I'm going to be using P total is equal to the pressure of the hydrogen gas plus the pressure of the water vapor. We're told that P total is 755 torr. That's equal to the pressure of the hydrogen gas plus the vapor pressure, which was 24 torr. P of hydrogen is equal to 731 torr. Now, I was asked the amount in moles of hydrogen. So that tells me that I'm going to be using P of hydrogen times V is equal to the moles of hydrogen times RT. Well, to be able to use that, because of the ideal gas constant, I've got to convert that 731 torr into atmospheres. 760 torr is equal to 1 atmosphere. So divide that 731 by 760 and you get a value of 0.962 atmospheres. I now can use the ideal gas law. My pressure is 0.962 atmospheres times the volume of 1.55 liters is equal to the moles of hydrogen times 0.0821 atmosphere liters per mole Kelvin times the temperature in Kelvin, which is 298 Kelvin. Solving for the moles of hydrogen, you get a value of 0.0609 moles of hydrogen. I want to back up to the previous question briefly, because I want you to note this is the process you used yesterday. You used Dalton's law of partial pressure to figure out the pressure of oxygen gas. You then used the pressure of oxygen gas to figure out the moles of oxygen gas. You had to do some stoichiometry in between to go from moles of oxygen gas to moles of peroxide, but then you would have used the molar mass to get to the mass of peroxide. So a lot of these steps are similar to what you would have used yesterday. Same thing with this problem. You used Dalton's law of partial pressure. In fact, this is almost identical to what you did yesterday. You then used the ideal gas law to solve for the amount of oxygen. So these are similar in nature to what you did yesterday in the laboratory. Let's look at another example. A 12.5 liter scuba diving tank contains helium oxygen, known as helix, mixture of 24.2 grams of helium and 4.32 grams of oxygen at 298 Kelvin. Calculate the mole fraction and partial pressure of each component in the mixture and the total pressure of the mixture. Okay. So the first thing we've got to do is we've got to convert the grams of each of these into moles. So 24.2 grams of helium needs to be converted into moles of helium, with the fact that 1 mole of helium has a mass of 4.003 grams. So we're talking about 6.045 moles of helium. We're also going to do that for oxygen. We have 4.32 grams of oxygen. Oxygen has a mass of 32 grams per 1 mole. So therefore, it's 0.135 moles of oxygen. The total moles is going to equal the moles of helium plus the moles of oxygen. So it's going to equal 6.045 plus 0.135, or in other words, it's 6.18 moles. Mole fraction of anything is equal to the moles of that thing divided by the total moles. So if I want the mole fraction of helium, it would be equal to 6.045 divided by 6.18, or in other words, it is 0.978. There is no unit to the mole fraction. Now, mole fractions add up to 1. So that means that the mole fraction of helium plus the mole fraction of oxygen is going to add up to the value of 1. So if the helium is 0.978 plus the mole fraction of oxygen, that adds up to 1. So the mole fraction of oxygen equals 0.022. Any questions about what I've done so far? All I've answered is calculate the mole fraction for each component. Mole fraction is the moles of that component divided by the total moles. So I had to get those pieces of information, which is what I did on the left-hand side of the screen. Now I need to calculate the partial pressure of each component. So for the pressure of the helium, it's going to be the pressure of the helium times the volume of the helium is equal to the moles of the helium times RT. The pressure of the helium is what we want to calculate. The volume was 12.5 liters. That's equal to the moles of helium, which was 6.045 times R, which is 0.0821 atmosphere liters per mole Kelvin, times the temperature, which was 298 Kelvin. So the pressure of the helium comes out to be 11.8 atmospheres. I'm double checking my math. Yes. Okay, for the oxygen, the pressure of the oxygen times the volume is equal to the moles of oxygen times RT, where the pressure of the oxygen is what we want to calculate with a total volume of 12.5 liters. That's equal to the moles of oxygen, which was 0.135 moles of oxygen, times R of 0.0821 atmosphere liters per mole Kelvin, times the temperature at 298 Kelvin. So oxygen has a pressure of 0.264 atmospheres. If I would have asked you for the total pressure, which I did, P total would be equal to the P of the helium plus the P of the oxygen, which would be equal to 11.8 atmospheres plus 0.264 atmospheres, which we get as 12.1 atmospheres. Questions? You will notice that again, I went back to the same ideal gas law. And I went to Dalton's law. These are common storylines. Now, yesterday you collected gas over water. It was a slightly different setup, but it was essentially like this. What we did in this particular case, they reacted zinc with hydrochloric acid. That produced hydrogen gas. The hydrogen gas traveled through the U-joint up into a container, and as it did so, it displaced the water in the container, but the water in the container, or the gas above the liquid level, really consists of two things. It consists of the hydrogen that was bubbled through, but it also consists of water molecules that have enough energy in order to break away from a liquid and become a gas. So it has some water vapor inside the tubing as well. And as you saw yesterday, the water vapor pressure is directly dependent upon the temperature. Again, the reason it's based off of the temperature is because you've got to supply it with the correct amount of energy in order to break the intermolecular forces so that the water can go from liquid phase to gas phase. And so the higher the temperature, the more likely you're to break those intermolecular forces so the liquid molecules can go into the gas phase. That's why as you increased the temperature, you increase the pressure of the water vapor. Now, yesterday, the table was given to you in torr, but I could have looked it up in millimeters of mercury as well. It's all dependent upon what I need. So let's look at one more example that is similar to lab. In order to determine the rate of photosynthesis, the oxygen gas emitted by an aquatic plant is collected over water at a temperature of 293 Kelvin and a total pressure of 755.2 millimeters of mercury. Over a specific time period, a total of 1.02 liters of gas is collected. What mass of oxygen gas forms? Okay, looking at this, we know that our pressure total is going to equal the pressure of the water plus the pressure of our oxygen gas. We were given P total of 755.2 millimeters of mercury. We can look up the pressure of the water at 293 Kelvin. Which is 20 degrees Celsius. And what we would see, looking back at this table, is that the pressure in millimeters of mercury would have been 17.55 millimeters of mercury for the water. Plus the pressure of the oxygen gas. So our pressure of oxygen is equal to 737.65 millimeters of mercury. Now, I'm going to use the ideal gas law because ultimately I want to know the amount of gas. I need to know in this case for the oxygen collected. So I'm going to convert that 737.65 millimeters of mercury into atmospheres with the fact that 760 millimeters of mercury is 1 atmosphere. So that is 0.971 atmospheres. We can now use PV equals nRT. Our pressure is 0.971 atmospheres. Our volume is 1.02 liters, is equal to the moles of oxygen gas times R, which is 0.0821 atmosphere liters per mole Kelvin, times the temperature of 293 Kelvin. And you get the moles of oxygen gas to be 0.0411 moles of oxygen. But we were asked for the mass of oxygen, so we're going to take that 0.0411 moles of oxygen, and we're going to convert that into mass of oxygen with the fact that there are 32 grams of oxygen per 1 mole of oxygen. So in other words, our mass of oxygen is 1.32 grams of oxygen. Yes. The 17.55, the first thing I did is basically that information came from this table. It said that it was 293 Kelvin, but this is in degrees Celsius. So the first thing I did was convert that Kelvin into degrees Celsius, and it came out to 20 degrees Celsius. So therefore, that's where that 17.55 millimeters of mercury came from. Does that answer your question? Other questions? Okay. So that's Dalton's law of partial pressure. Now, folks, we're getting moles. And if you'll recall, moles lets us do some stoichiometry. Because you saw a variation of this diagram. I've given you multiple variations of this diagram. But now I'm going to add one more piece to this puzzle. You can take the ideal gas law and you can convert that in to obtain moles given. Once you have moles given of one of your reactants or products, you can convert that into moles of the second material using the mole to mole ratio that we have been using in stoichiometric calculations. And then once you have it in moles of that second material, you've got options. We can get to the molar volume, we can get to the molar mass, we can get to the number of atoms or molecules. But it all started with taking the gas law and getting it in the mold. Getting the mold. So we're just adding new pieces to this. So let's look at an example. Methanol can be synthesized by the reaction where carbon monoxide reacts with 2 hydrogen gas to form methanol. What volume in liters of hydrogen gas at a temperature of 355 Kelvin and a pressure of 738 millimeters of mercury is needed to synthesize 35.7 grams of methanol? Okay, so we have been asked to determine the volume of hydrogen gas. We never do anything with the substance we have the question about. We always start our calculation with the substance we know things about, which is or know everything about, which in this case is our methanol. So we're going to take that 35.7 grams of methanol, and our first task is going to be to convert that into moles of methanol. We convert the mass of methanol into moles of methanol by using the molar mass of methanol, which is 32 grams of methanol is equal to 1 mole of methanol. Now that we have it in moles of methanol, we can convert it into moles of hydrogen. For every 1 mole of methanol, we have 2 moles of hydrogen. So 35.7 divided by 32 times 2 means we have 2.23 moles of hydrogen. Okay, that basically gave us N. We want to know V. We are given the T at 355 Kelvin and the P at 738 millimeters of mercury. We're ultimately going to use the ideal gas law because we have a P, V, N, and T. But to do so, we need R, which is 0.0821 atmosphere liters per mole Kelvin. Now, before I can use these numbers, I've got to make sure all of my units match. Right now, everything matches except for the pressure. And so I need to convert the pressure into atmospheres by dividing by 760. And so it is 0.971 atmospheres. Now I have all parts of my ideal gas law. I have the pressure. The pressure is 0.971 atmospheres. I am asked to calculate the volume. That is equal to the moles of 2.23 moles times R of 0.0821 atmosphere liters per mole Kelvin times the temperature in Kelvin of 355 Kelvin. solving for this equation. You get a volume of 66.9 liters. For our hydrogen gas at 355 Kelvin. Let's look at another example. In the following reaction, 4.58 liters of oxygen was formed at a pressure of 745 millimeters of mercury and a temperature of 308 Kelvin. How many grams of silver oxide decomposed? We have been asked to figure out the grams of silver oxide. We are told that we have 4.58 liters of oxygen at a pressure of 745 millimeters of mercury and a temperature of 308 Kelvin. What this tells me is I'm going to be using the ideal gas law to get to N. Okay, but before I can do that, I've got to make all of my units match R, which means I've got to convert that millimeters of mercury into atmospheres. And I take 745 millimeters of mercury and divide it by 760 millimeters of mercury to 1 atmosphere. And so it's 0.980 atmospheres. Now we're going to take our PV equals nRT and get to moles of oxygen. So our pressure is 0.980 atmospheres times the volume of 4.58 liters is equal to the number of moles of oxygen gas times 0.0821 atmosphere liters per mole Kelvin times 308 Kelvin. Calculating this out, you get moles of oxygen equal to 0.177 moles of oxygen. Now that I have moles of oxygen, I can use mole-to-mole ratios and stoichiometry. So I'm going to take that 0.177 moles of oxygen and I'm going to convert that into moles of silver oxide by the fact that 1 mole of oxygen is produced for every 2 moles of silver oxide that react. Of course, I was asked for the grams of silver oxide. So I need to multiply this times the molar mass. And it comes out to be 231.8 grams of silver oxide is 1 mole of silver oxide. So we're looking at 82.1 grams of silver oxide. Folks, this is the other portion that you did yesterday. Once you use the Dalton's law of partial pressure, you then calculated your moles of oxygen using PV equals nRT. You then took the moles of oxygen, but you converted it into moles of peroxide using the mole-to-mole ratio from the balanced chemical equation. You then converted it into grams of peroxide using the molar mass of peroxide. So in other words, this is the process that you were doing yesterday. I just did it for a different substance. Let's look at one more example. How many grams of water form when 1.24 liters of H2 at STP completely react with oxygen? I have 1.24 liters of H2 at STP, meaning that it's 1 atmosphere and it is 273.15 Kelvin. I have the information here because I've got VPT. I have the information to calculate N. So I'm going to use PV equals nRT to calculate the N for hydrogen. So 1 atmosphere times the volume of 1.24 liters is equal to the N of hydrogen times 0.0821 atmosphere liters per mole Kelvin times the temperature in Kelvin, which was 273.15 Kelvin. So your N of hydrogen is 0.0553 moles of hydrogen. So now I can get to the water because I can take and do some stoichiometry. I can take that 0.0553 moles of hydrogen. I can use the fact that for every 2 moles of hydrogen, I make 2 moles of water. But I was asked for the grams of water, so I'm needing to use the molar mass of water in order to convert that into grams of water. So when you complete this calculation, you get 0.995 grams of water. That's how much can be formed from 1.24 liters of hydrogen gas at 1 atmosphere and 273.15 Kelvin. Questions? I tried to give lots of examples today. One of the things I'll try to do today is I'm going to also try to get your homework put together for Tuesday so that you can get a jump on it if you so desire, so that maybe you won't have to do that next week.
Okay,